So Professor Cynthia Rudin is a past chair of both the Informed Data Mining section and the Statistical Learning and Data Science section of the American Statistical Association. She has also served on committee for DARPA, the National Institute of Justice, AAI, and ACM, CKDD. She has served on the 3 committees for the National Academies of Science, Engineering, and Medicine, including the Committee on Applied and Theoretical Statistics, the Committee on Law and Justice, and the Committee on Analytics Research Foundation for the Next Generation Electric Grid. She has given keynote invited talks at several conferences, including KDD, AI, ST code, machine learning in healthcare, fairness, accountability, and transparency in machine learning, and the Nobel conferences. So today, she's going to present about scoring system, and the title of her presentation is Scoring System at the Extreme of Interpretable Machine Learning. After a talk, you could, of course, ask your question. I will chair the session. So, Cynthia, thank you very much for being here. You can begin now.
Thank you. So I'm a computer scientist, and I work in interpretable machine learning, which means I'm trying to design models that machine learning models that humans can understand. And I'm going to talk about scoring systems today, which are really tiny little models at the extreme end of interpretable machine learning. It's really hard to believe the power of a little itty bitty model. So before I talk about scoring systems, let me ask you a question. Can a typographical error lead to years of extra prison time? Right, this should never happen, right? Typos making decisions, that's crazy. You know, who's making decisions here, a judge or a typo? And is that fair if that happened? But it happens all the time. And so this is an article about a person who was denied parole because of a miscalculated compass score. So he was in prison, this is Glenn Rodriguez, he was in prison since he was a kid, and he comes up for parole and his parole is denied. And it turns out that there was a mistake, a typographical error on his score sheet for his criminal history features. And he was denied parole, and there was nothing he could do about it because he didn't know about the error until afterward. So just some definitions. A black box model, black box machine learning model, is a formula that's either too complicated for any human to understand or it's proprietary. Whereas an interpretable machine learning model obeys a domain-specific set of constraints so that humans can better understand it. Okay, so when do we need interpretable machine learning? We need it anytime it would be really bad if the model went wrong, right? For high-stakes decisions or when you really need to troubleshoot the model. So for criminal justice models, credit scoring, air pollution, airplane maintenance, basically and like I said, anytime it would be really bad if the model went wrong, because a lot of times the AI models really do go wrong. They go really badly wrong. So we already know that we could send people to prison based on typos, but what else happens? So I've put up here 2 of my favorite articles where black box AI models went wrong and no one was able to figure out what happened. So the article on the left, this is from when a black box AI model told everyone that air quality was fine during the California wildfires in 2018. And the model said it was safe to go outside when it definitely was not. And then the article on the right is about how FDA approved AI models for healthcare are not performing as well as they should, and no one knows why. So these are deep learning models for detecting intracranial hemorrhage. And again, they were FDA approved, so they were approved by our Food and Drug Administration, and yet when they launched them into the real world, they didn't work and no one knows why. Now, I've given you just a few things that have gone wrong with using black box models, but there's a tremendous amount more that could go wrong. And probably many things have gone wrong that were hidden, so I don't know about them. And now people are starting to use machine learning for medical decision making, for loan decisions, for self-driving cars, and all manner of other things that you really don't want to go wrong. And some people love their black boxes. They argue fiercely that they need them. Anyway, I want to get back to COMPAS. So do we really need to have black box models? Are they more accurate? And luckily, there was a data set from Florida that was released that could tell us exactly how accurate COMPAS is. Okay, so we took that data, which had the COMPAS scores for a few thousand people in Florida, and it had basic criminal history and demographic information of those people. And we took that data and those COMPAS scores and compared the accuracy of the COMPAS scores to the latest machine learning model we had developed in our lab at the time, which is called Corals. We've done a lot more than Corals since then. Corals is a very complicated algorithm, but it produces very tiny little models. Anyway, so we put these things head to head on this data set. And the model that Corals produced on the data was just really, really tiny. It was so tiny it could fit on the bottom of a PowerPoint slide. So this is the model. It says, if the person's age is between 19 to 20 years old and they're male, then predict arrest within 2 years of their COMPAS score calculation. Also, if they're 21 to 22 and they have 2 to 3 prior offenses, then predict arrest within 2 years of their COMPAS score calculation. Also, if they have more than 3 priors, predict arrest, otherwise predict no arrest. And we looked at this and we thought, oh dear, could this possibly be as accurate as COMPAS, right? This is a model sold by a company that could use up to 137 factors in it. And, you know, the surprising, could this really be as accurate? And the surprising thing is that it was. So here I'm showing you tenfold cross-validation results. The colors are from different test folds. And as you can see, both of these models are about equally accurate, okay? So we said, great, all right, we're getting equally accurate results with these things. What would happen then if we threw the whole machine learning arsenal at this problem? Okay, so I'll take the whole, can we get any more accuracy if we throw everything we've got at it? So we did, and we didn't get any more accuracy. Okay, so these algorithms, some of them produce models that are so complicated that there's no way you could put them on a PowerPoint slide. Like this is boosted decision trees, support vector machines with radial basis function kernels, random forests, right? These are super, super complicated formulas. Whereas, Corals, it's just right on the bottom of the slide right there. So there was this huge debate after the COMPAS data became public about algorithmic fairness of COMPAS. But the truth is that we just don't seem to need COMPAS at all. Now, you've seen that black box models aren't always more accurate than simple models, but there's some more important general knowledge that I need to provide you. There's really 2 broad kinds of problems that we encounter in machine learning and data science. There's problems with tabular data and problems with raw data. And tabular data look kind of like the criminal justice data that I just showed you, and here's a medical example here. And raw data could be like, images or sound waves or text, large amounts of text where, these data already come with a good representation. These don't, okay? So they're different. And they use different types of techniques. And the definition of interpretability is different, okay? So they're really quite fundamentally different. So for the raw data, neural networks is the only technique that's working right now. And that doesn't mean that that's always going to be the way it is, but right now that's the way it is. And that doesn't mean that you can't be interpretable. You can, but you have to think about what interpretability means. Whereas with tabular data, it's totally different. In fact, tabular data problems resemble the COMPAS data that I just showed you. And with minor preprocessing, all the methods tend to have similar performance. And you're not really getting any gains from neural networks or more complicated models. And so what that means is that even very sparse models can get up to the accuracy of these much more complicated models, which is really interesting. So while we work on interpretable neural networks for these problems, which is obviously a task a lot of people are thinking about right now, including me, we have to realize that there are tremendous opportunities on the tabular data side to create models that are really accurate, but also really interpretable. But you have to optimize the models well in order to get up to the accuracy of the black boxes. You can't just do whatever. You actually have to optimize for them and find good models. Okay, so if we think about the history of predictive modeling over the last century, only a small amount of that time did we have data. So most of the predictive models needed to be created by humans. So when we think about what kinds of predictive models we want to build now that we have data, and we want these models to be interpretable to humans, we need to think about what types of models humans designed in the absence of data. And the most popular form of predictive model, hands down, in this whole time period, was scoring systems. Okay, so a scoring system is a sparse linear model with integer coefficients. And what I've put up on here is possibly the most widely used predictive model in healthcare, maybe this in the APGAR score, I don't know. But it's a model that predicts stroke in patients with atrial fibrillation. This model, you add up points. Those points give you a score. The score translates into a risk. And this model is not a machine learning model. It is not created from data. It was created by humans. It was validated on data, but it was created by humans. Now, scoring systems have been used for about 100 years, okay? So I'm putting up here the Burgess paper on determining success or failure on parole. So what Burgess did is I'll just read it right here. It says, accordingly, 21 factors were selected by which each man was graded in comparison with the average for the 1,000 cases upon the probabilities of making good or failing upon parole. So in other words, he created a scoring system where he picked 21 factors himself, and people get points based on whether they obey these factors. And those points, when you add them up, translate into a risk of success or failure on parole in 1928, okay? And he had this table in his paper where he converted the scores to probability. So if you had like only 2 to 4 points, you have only a 24% chance of being a non-violator of parole, okay? And then 16 to 21, you had a 98.5% chance, all right? So they had this table. He also did some really interesting stuff where he sort of took the population and divided them into these interesting groups. So here, like, you had ne'er-do-wells and mean citizens and drunkards and gangsters and recent immigrants, oh my goodness, and farm boys and drug addicts. It's just, we don't do this exact type of thing right now, which is probably good. But we do still have scoring systems. We still have the same, it's the same idea that's still used. So here's an example. This is the Pennsylvania Commission on Sentencing's model from 2013. And again, you get points. Those points translate into a risk of being arrested. So it's still the same types of models. Why? It's because they're easy to use and easy to understand. And then this is the violence risk appraisal guide where, again, you get points. I'm just zooming in there. Get points, you add up the points, and then that translates into low, medium, or high risk. And then in medicine, there are tons and tons of scoring systems. There are even whole websites you can go to that have scoring systems sorted by medical specialty. So if you scroll down to neurology and you go click on seizure, then you might find you'd find like 3 scoring systems for seizure prediction. So you click on one of them, so you click on the 2 helps 2B score, and then you get this kind of table, and you punch information into this calculator, which is actually just a scoring system, and you get points, which translate into a risk of seizure in the next 6 hours. And the problem, of course, with these scoring systems is that when you design them by hand or using heuristics, they aren't very accurate. So of course, the question I'm going to be asking is how to design these scoring systems to have optimal predictive performance according to data, but also be, understandable and easy to use by humans, right? And the thing about the 2 helps 2B score that makes it different than all of the other medical calculators is that it was not designed by humans or using heuristics. And now I want to talk about this application for a while because it's really important. So let's say that you have an aneurysm in your brain that bursts. And so you have a hemorrhage in your brain. There's blood, like a blood explosion in your brain. And you would go immediately to the emergency room. The doctors would do surgery and fix that up. And then they would put you in the intensive care unit where your whole head would be covered in continuous EEG monitors. Okay. So why are they monitoring you? And the answer is they're monitoring you for the possibility of seizures. Now, these seizures are common. About 20% of critically ill patients get them. Seizures cause brain damage and death. They are very scary, to the point where doctors will even give you medicine to shut off part of your brain to prevent you from getting a seizure, because those seizures, like I said, they cause brain damage, they cause death. They're very, very dangerous. They can be even more dangerous than the original injury. And the only way to detect seizure-like activity is to use EEG. But the problem is that EEG monitors are a limited supply, right? There's not enough monitors or doctors to read those monitors. And so what happens is the monitors stay on patients way too long, and then patients who need them don't get them. And so we need EEG to predict seizures and to determine the duration of necessary EEG monitoring so that we can allocate resources well. Okay, so I worked with neurologists to create the 2 helps 2B score. So it's the same one that we saw in Medscape. So that was us who created it. And it's now widely used in hospitals. And it's small enough that it can fit on a PowerPoint slide, but it's as powerful as our best black box machine learning models. And if you enter the information into the screenshot we saw earlier, it'll compute the 2 helps 2B score. So it's just like this. And it's called 2 helps 2B because it's 2 HELPS and then 2 points for the B, so that the doctors can memorize the whole model just by knowing its name. Okay, so 2 helps 2B. It looks like a rule of thumb, but it actually was not created by doctors. It was created by data fed into an optimization problem. It is a full-blown machine learning model. Okay, it's not just a rule of thumb. It's just as accurate as black box models on our data set. I know it says that we have only 6 factors in here, which is true. The model has only 6 factors, but those 6 factors were chosen from a database of over 70 factors. And the algorithm chose which 6 factors to include and how many points to include. And then the points translate into it. Like I said, you add out of the points, you get a score. The score translates into a risk using the table below. Okay. All right. And doctors can decide themselves whether to trust it. It's not like a black box where you have to just trust it. Like here, the doctors can look at it and decide themselves whether to trust it. Doctors can also calibrate the score with information that's not in the database. So for instance, if the doctor looks at the patient and says, oh, well, you have a condition that's not in the database. I think you need an extra point for that. Then they can do that. And the score can be explained to non-physicians. So you can explain to someone why their relative is being taken off of EEG monitoring, for instance. Okay, and as I mentioned, there were a large number of variables in the database. And of course, what that leads to is the fact that there's a combinatorial explosion in the number of models to choose from. Now, I know the model that I put up on the previous slide, like the 2 helps 2B score, I know it looked really easy. It looked very simple. And you might be disappointed and say, well, but that's not what I expect of a machine learning model. That's too easy, that problem. But the truth is that designing an optimal scoring system is not easy, right? There's a combinatorial explosion in the number of model options to choose from. So, what are the challenges when we're designing these things? Well, first of all, we want the model to be as accurate as the best black box. We want it to be sparse so that a doctor can memorize it by knowing its name. We might have additional constraints that we want to add, like constraints on a false positive rate or fairness constraints or whatever. And we want to have integer coefficients because, we want numbers like 1, 2, and 3 and not like 27, for instance. We want the same thing as what people have been doing since 1928. Now, typical approaches for solving this problem and constructing scoring systems are, first of all, to use a panel of experts, like for the CHADS2 score, where they asked a lot of doctors, or they had a bunch of doctors kind of creating this model and then validating it afterward. And then the other fairly common type of approach is to fiddle with logistic regression coefficients. So basically it's like an ad hoc kind of framework where you just grab a bunch of features, then you do logistic regression, and then you scale the features, you round the features, and then you're like, well, I don't like that, I'm going to switch out that feature for this other feature, and then you do that, and then you fiddle around with round everything. It's a lot of fiddly business. And the problem is that those methods don't work. They produce suboptimal scores, and they rely on humans to do high-dimensional constrained optimization, which is not a good idea. Okay. All right, so let's just see what would happen if we tried this ad hoc approach, okay? So here's an elastic net model for the seizure prediction problem for just a few hand-selected variables. But it's difficult to use because if the patient has, like, let's say they have prior seizure and they have patterns superimposed with fast or sharp activity, then okay, how far is their score from 0? And what would need to happen to get their score to 1.6? Can you memorize this model and use it on a patient as you're dealing with a million other things? Probably not, right? Especially if the model has more variables in it, it just would be much more difficult to calculate counterfactuals and things like that. Okay, fine. So let's try rounding the coefficients. Okay, let's try rounding them. And here's what we get. That didn't work. I lost almost all the signal, and my probabilities are a mess. Okay, let's try it again. This time, I'm going to scale all the coefficients by multiplying them by the best factor I can and then rounding. Okay, so I did that. It's again not very accurate, and it really isn't quite what I'm looking for. It looks better, but it's just not as accurate as the 2 helps 2b score. Maybe if I fiddled with it some more, I could get something better, but it would be really hard to get something as nice as the 2 helps 2b. And regardless, fiddling is not what we should be doing in this case. We should be actually formulating and solving an optimization problem to get the answer. Okay, so let's say that computation is not an issue. Okay, let's say we have infinite computation. What optimization problem would we solve? And I claim we should solve this one. Okay, so this problem has 3 terms in it. The first term is the logistic loss, which keeps the model accurate and calibrated to the data. The second term is a model size term, so that says please keep the model small if you can. Try not to include too many factors in it. And then there's a set of constraints down here, which says that the coefficients need to be small integers. And here it says you can be any number between -10 and 10. As you saw, the 2 helps 2b score had only 1, 1, 1, 1, and 2. That's what the algorithm chose. That wasn't something that we manually chose. That was what came out of the solution to this problem. Okay, and then you can put your additional constraints in there if you want, like fairness constraints or whatever. Okay, so this problem, if you're an optimization expert, you'll know immediately this problem is really, really hard. This is a mixed integer nonlinear program. There are no, easy solutions to this problem. It's hard. Okay, and then if I write it down this way, writing it down this way, you can see geometrically why the problem is hard. Okay, so let's just take the logistic loss and the integer coefficient. So let's forget about that term for now. Let's set c to 0, and then let's just look at this and that. And I'm just going to plot it in 2 dimensions. So let's just say that this is coefficient 1, that's coefficient 2, and then the logistic loss are the level sets of logistic loss are these kind of like ovals, because logistic loss is convex, so they're going to be convex sets. And then this is the logistic loss solution, and as you can see, that is not at integers. So what would happen if you rounded? Okay, so if you rounded, you would go against the performance gradient and you lose a whole lot of performance no matter how you rounded. When in fact, at the same time, there is a solution over here that actually has a very low loss, and its solution is integer. You have integer coefficients as the solution, okay? And you could say to me, well, you know, the only reason this works is because you have these long, skinny areas of low loss. And you could say that's unrealistic, but it's not. It's very realistic. And, you know, that's the whole reason for the whole field of mathematical programming, because most problems are like this. And if you have constraints, those constraints make the problem even harder, because then the rounded solutions can violate the constraints. Like if you say there can't be any solutions over here, but then if you round, you might get a solution that violates the constraints. So you can see why it's actually useful to solve the optimization problem. And the solution to it gives the 2 helps 2b score. Okay, so after solving the problem, okay, and I'll tell you how we solve this problem in a minute, right? I'm going to go through actually the mathematical kind of how we did that. But after solving it, we go back to 2 helps 2b and we can help patients, right? So now the patient comes in with their aneurysm, bursts, they have their hemorrhage, they get their surgery, they're being monitored in the intensive care unit, and now the doctor looks at their EEG and says, oh, the patient has this, this, and that. That's a 2 helps 2b score of 3. They're high risk. And so I'm going to place them on continuous EEG for at least 72 hours and start them on preventative medication for seizures. Now, so far, 2 helps 2b has been validated on an independent multi-center cohort. This is not a study that I was involved in. This was done by neurologists. This is the predicted probability of seizure, and that's the true probability of seizure. And so we want to be on this line as much as possible. Now, the blue data is from the initial study that we built 2 helps 2b on, and then the green data is from the validation study at different institutions. And so what you can see is that it generalized very nicely across institutions. And currently it's used at several different hospitals. And in the validation study, it's resulted in a substantial reduction in the duration of EEG monitoring per patient, which has allowed the doctors to monitor a huge amount more patients than before, 2.82 times more patients. And according to the doctors, this really helps them prevent brain damage and save lives. Okay, so I want to talk about the machine learning algorithm that produced 2 helps 2b, which is called RiskSlim. And RiskSlim uses the lattice cutting plane algorithm that I'm going to tell you about now. And it solves this difficult optimization problem. But before I tell you how RiskSlim works, I need to tell you how cutting planes work, because RiskSlim it uses a cutting plane algorithm. So I need to tell you what cutting plane algorithms do in case you don't know. And I also need to tell you why traditional cutting plane algorithms don't work. And I need to do that before introducing RiskSlim. So that's what I'm going to do. I'm going to introduce traditional cutting planes, tell you why they don't work, and then tell you what the fix is. Okay. So let's say that we have just the logistic loss, which is convex and non-negative, and we want to minimize it, okay? So to do that, if we're doing cutting planes, we would start somewhere, just pick there, starting there. Then we compute the function value and the gradient and create a cut, like that. Now, this blue thing is like a surrogate for this function here. Okay, so I'm supposed to minimize the blue thing, but it goes below 0, and I know my function does not go below 0, so I'm going to pick this point to be my next point. Okay, do it again. Compute the function value and the gradient, create a cut. Minimize the blue thing, pick our next point. Repeat. Okay, so here's our next point. Again, create another cut. And you keep going like this until eventually it finds a solution. And it realizes that it found a solution because the minimum of the objective equals the minimum of the surrogate. And then when that happens, the algorithm knows it's done. It knows it's found the minimizer of the objective. Okay. Now, this all sounds well and good, but something goes terribly wrong with it when you're creating models with integer coefficients. So let me show you where that happens. So if you're here in the computation, you've iteratively constructed this surrogate, and when you minimize it, you land here. So you can see that minimizing the surrogate involves solving a linear program, because you see these are lines. So this is a linear program. Linear programming problems are very easy to solve, so that's good. But the solution, though, might not be at an integer. That's where the problem is. The solution needs to be at an integer. So the solution might be here, but we actually need it to be over here, because remember, the coefficients have to be integers. So the solution we actually want then might be here. All right, so that means if you want all the coefficients to be integers, right, then the feasible region is the integer lattice. And you're solving a mixed integer program at every iteration and not a linear program. And MIPS are much harder to solve than LPs. And you've got to find a point, you got to find a point on the lattice that minimizes the objective, right? You need to solve that MIP to optimality at every iteration, because otherwise you have no idea if you've solved the problem. And still, every iteration you're adding a cut. So as you add more and more cuts, the MIP that you have to solve becomes bigger and bigger and bigger. And if you know anything about MIPS, if you've ever tried to solve a MIP, you know that you cannot solve big MIPS. It just does not work. These problems are too computationally difficult. Right? No matter how big or small the data set is, after you add a couple hundred cuts, the problem becomes really difficult for the solver and it stalls. So this is what happens. So after about 70 iterations, this isn't even a big problem. This is a really small problem we were working on. And here, the MIP just can't solve it. It just spent over 10,000 seconds per iteration, and we just had to turn it off because it just wasn't getting us toward a solution. It was just taking forever. And then the optimality gap, which is supposed to go down towards 0, it just stayed up at 100. And so it's just completely stuck. So we designed a cutting plane method that does not stall. Okay. So with this new algorithm, at every iteration, instead of solving the MIP from the surrogate, it solves the linear program. It solves the LP, which is much easier to solve. And it gives you this solution, but then what do we do with that? Because it's not feasible, right? This is not an integer. So what do we do? Well, if it happens to be an integer, like just serendipitously, then I can add a cut, right? If the LP solution happens to be right on top of one of those integer points, great, it just solved the MIP serendipitously, so I add a cut. Okay, so that's one thing that could happen. I could get lucky. But if it doesn't land at an integer point, well, you know that there's no feasible solutions in here, so you can just cut this whole part of the space out and then iterate separately in each of the two pieces. Okay, so you can just divide the whole problem into two pieces and say, look, I know there's no solution in here, so I'm going to cut this whole part of the search space and I'm going to solve two separate problems, this problem and this problem. I'm going to solve them separately. And then at the next iteration, I solve an LP on each side. And as you can see, I serendipitously solve the MIP here and I get to add a cut. And same with this side too. Okay, so we continue to do this. So at every iteration, we either accidentally serendipitously solve the MIP and I get to add a cut, or I'm getting a solution that is infeasible, in which case I just subdivide into two separate problems. Okay, great. So this actually seems to really completely solve the problem. There is just no stalling for the lattice cutting plane algorithm that I presented. And even after 10,000 iterations, the solver can still finish in under 100 seconds. It never stalls, and the optimality gap goes gracefully down to 0, which is exactly what we wanted it to do. Okay, so it provably converges to the optimal solution. All right, so just in case you missed that, let's do it again very quickly on this one slide. So if you have your objective you're trying to minimize, it's smooth and convex. You iteratively construct the surrogate, cutting plane approximation, and then what you do is you find the solution to the LP, you're really happy, because it didn't take very much computation, but then you realize, oh crap, it's not feasible. It's not in an integer, so you're actually kind of sad. And so what you do then is you subdivide the space into two separate problems, one where you have a constraint that coefficient is less than or equal to 5, and the other constraint, which is that the coefficient is greater than or equal to 6, and you solve these problems separately. Okay, cool. And then there are just two options when you solve the optimization problem. If when you solve the LP, if the subproblem leads to a feasible integer solution, like 6 or 5, then you got to cut. Otherwise, you split into two subproblems. Okay, and that's the technique. All right, now LCPA, the lattice cutting plane algorithm, that's the only method that generates solutions within a reasonable time. If you try to take this problem and you send it into a generic mathematical programming solver, it will just choke, and it'll take till the end of the universe to solve even a moderately sized problem. And if you try to use standard cutting planes, well, as we know, it doesn't work. It just stalls because it requires solving larger and larger mixed integer programs. Okay, so we developed this algorithm, and it works. And so we didn't just use it for seizure prediction. We actually used it for a whole lot of other problems where we collaborated with doctors. So we used it for ADHD screening, sleep apnea screening, and then the clock drawing test. This is interesting. So here, the patient uses a digital pen to draw a clock and then copy a clock. And then the algorithm keeps track of the timing information, like how long it took you to draw each part of the clock, and whether you had very subtle little hooklets on the end of your pen strokes to indicate that you were thinking about where you were going. And it combines all that information into scoring systems. And we also wrote a paper about recidivism prediction, where we claimed that you didn't need black box models to predict recidivism. And this paper got into the center of a battle as to whether black box models are more accurate in criminal justice applications. So stay tuned for that. All right, now the question everyone keeps asking me is whether interpretable models are really as accurate as black box models. Now, the way that we answer questions like that in the machine learning world is to compare algorithms by looking at benchmark data sets. Okay, so here's a great benchmark. Okay, this is the Explainable Machine Learning Challenge dataset provided by Fico. It's a HELOC dataset. It has credit scoring information for 10,000 people. It's actually quite a detailed data set. Okay, so it's 10,000 loan applications. Half of them default on their loan and the other half don't. And your job is to figure out which people are which, right? It's to predict for a new loan applicant whether or not they'll default on their loan. Now, and the organizers of the competition, they told us, well, when they gave us the data set, they told us, create a black box and explain it. Okay. Because they didn't think there could be an interpretable model that you could construct from this data. If you run a whole bunch of black box models on the data set, you get this accuracy and this AUC. So these are the two performance metrics, right? This is area under the RSC curve. This is accuracy. These are the two performance metrics we typically look at in machine learning, okay? So that's what we got to get to with our interpretable models. All right, so IBM, which got first place, they provided a very tiny little model with only 6 questions, but they broke the golden rule of interpretable machine learning. They lost accuracy, they lost performance. Okay, so their accuracy went down a bit, but their AUC just, this is just bad. Because like AUC is between 0.5 and 1, and here they got a 0.62, which is really bad compared to the 0.8 that we know is possible. So our entry, which won the Fico Recognition Prize, didn't lose any performance. We got an accuracy the same as the black box, AUC same as the black box. And the model was actually very simple. It was like 11 scoring systems. It was like we divided the features into 10 categories, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. With each category had 1 to 4 features each. I'm just going to zoom in on the largest model, which had 4 features. which is the delinquency score. So delinquency was based on sort of percent of trades never delinquent, months since most recent delinquency, maximum delinquency in the last 12 months in public record, whatever, you know. Okay, so basically, this is what this model is. It's just a tiny little scoring system. Well, it's really an additive model for these 4 factors. Okay, so you put your information in. Here's a person whose information I put in there from the data set. This person, not so good. Like, the person was delinquent fairly often on their trades, right? The percent of trades never delinquent was only just like between 59 and 84. So this person was fairly often delinquent on their loan or trade, their trades. And then this is months since most recent delinquency, but this person had a delinquency very recently, like within the last 8 months, okay? So they get points for all that, and those points get added to a bias score, and then those get added up and become a risk of 79.8%. Okay, so here, and that 79.8 comes from taking the sum of these two, sticking it through this function, get 79.8%. Okay, so that's how it's literally just 10 models like that, like tiny. Some of the models only involved like one feature. So they were very small models, and then we had all 10 of them combined to form the final model in just one 10-item logistic regression model. Okay, so yeah, what we found is that even on challenging benchmark data sets, the interpretable model's accuracy equals the black box accuracy. All right, so I want to go back to the topic of criminal recidivism and the COMPAS score. And now, as I said, this paper got into the center of a battle as to whether black box models are more accurate in criminal justice applications. Okay, so something you need to know here is that explaining a black box is not the same at all as creating an inherently interpretable model, right? If you create a model to approximate a black box, that is an approximation and not an explanation, because the black box and the explanation could use totally different variables, right? If variables are correlated with each other, the explanation could use one set of variables and the black box could use a different set of variables. So it's entirely possible that you could make the mistake of thinking that whatever the approximation depended on, the black box would also depend on, but that is not true. In fact, it is possible that you could create a approximation for a black box model that depends on age, priors, and race. And then you could assume then that because the approximation depended on race in addition to sort of age and priors, that the black box would also depend on race. Okay, you could assume that, but it may not be true, right? The black box might only depend on age and number of priors. And you could say, well, nobody would make this mistake. Like, nobody would ever approximate a black box and assume that because the approximation depended on race, that the black box depended on race. Like, nobody would do that. But it might happen. And it did happen. And it happened exactly with the COMPAS score. So, and that's exactly what happened in the famous machine bias article, the ProPublica article that everyone talks about. So this is exactly what they did. They took COMPAS, which is a black box, they don't know what's in it. They approximated it with a linear model that depended on age, priors, and race, and then they concluded that COMPAS depends on race in a way that's different from dependence on age and priors. So let me just go into a little more detail about this. Okay, so what ProPublica actually did was they showed that the false positive rates and false negative rates of COMPAS varied by race. And so they suggested that that might not be a good comparison because the demographics of the whites and the blacks in the database were very different, okay? And the reason that they're different is due to systemic racism in society. Okay, so that's why age, race, and criminal history are all like correlated with each other, right? Because of systemic racism. Okay. So ProPublica knew that, And so they said, well, you know something, maybe we shouldn't just look at FPR and FNR. This is maybe not a good idea. We should condition on age and number of priors and see that, see whether compass depends on just age and priors, right? Or whether there's something more in it. So then they did a linear regression model that included age and number of priors and race. And they still found a linear approximation to compass with a low p-value for the race covariate. And so then they concluded that compass depends on race in addition to the way that it depends on age and criminal history, which are correlated with race. But the problem is that I don't think compass is linear, and so I don't think their conclusion follows from their analysis. So let me show you why ProPublica's assumption was particularly bad. So we took the data from Florida that was used in the ProPublica piece. So this is the same compass data set that I talked about at the beginning. And we plotted it. Okay, so this is compass as a function of age. And each dot here is a person. It's their age and their compass score. And as you can see, there's a pretty sharp curve here. Like somebody who's 20 years old is not going to get a compass violence score of -4.5, right? You're not going to see that. And so we think that these might be the minimum compass score you could get for each age. And there were some outliers. I mean, maybe a few typos in the data set, but overall not pointing to a linear function of age, okay? And it looks like compass heavily depends on age here, okay? So, there's just no real way to create a linear function of age that makes any sense there. So if compass does depend heavily on age, which we think it does from this figure, and if ProPublica messed up the dependence on age, that could definitely mess up their analysis. Okay, so what we decided to do was subtract out this very, obvious, like nonlinear dependence on age. Just subtract it out and say, okay, we're going to take into account that nonlinearity, and let's see if we still get the compass looks like it depends on race in addition to age and criminal history. Okay, so does compass minus our age function depend on race? And in order to figure that out, we ran machine learning with and without race, and it doesn't seem to, right? We ran machine learning methods with and without race to see if they need race to predict compass well, and they perform similarly. So race actually does not, it's not a useful factor in predicting compass. So, just like in our interpretable recidivism paper, race is not a useful predictor of recidivism, other than through correlations with age and number of priors. So ProPublica's conclusion here is pretty shaky. So then if race doesn't actually appear in compass, other than through its correlation with age and criminal history, then how did they find these pairs of people, right? These examples, these were key evidence on how compass depends on race, right? Because the white person had a much longer criminal history, like pretty deep criminal history. And the black person had a couple of misdemeanors and gets this like super high compass score, right? How did that happen? The thing is, if you look at these two people, the black person is much younger than the white person. And I'm not saying, look, this guy, Vernon Prater, he's old, so he doesn't get the age points. And I'm not saying that I agree with this, but if they had compared two people of the same age, it would be much more convincing that compass depends on race in addition to the strong dependence on age. So ProPublica's claims not really holding up with respect to race. So compass might not actually depend on race, but I think there's a much worse problem with compass that ProPublica completely missed, which is that humans are not very good at entering data reliably, which is what caused the issue with Glenn Rodriguez. So if you have 137 factors entered by hand for each survey, which is what you have on a compass score sheet, even if you have a 1% error rate on data entry, there's at least a 75% chance of at least one typo on a survey. And this is a serious disadvantage to complicated or proprietary models and causes a level of noise in the criminal justice system that affects everyone who goes through it. So, like I said, it's exactly what happened to Glenn Rodriguez. So we were looking at the Florida data to try to figure out how often these typos might happen. And we found some really strange inconsistencies in the data. So here I'm showing you a bunch of people that have the lowest possible compass violence decile score. So decile scores are 1 to 10. 10 is the worst, 1 is the best. So these people all had a compass violence decile score of 1. But look at their criminal histories. I mean, you know, come on, right? Aggravated battery with a deadly weapon. You know, resist, obstruct officer with violence, attempted first-degree murder, first degree. I mean, how in the world do these people get the lowest possible compass violence score? I can't explain this other than some kind of weird data issue. I don't know what it was, but I can't explain it other than that. And that's only the tip of the iceberg. Here's people with compass scores 2 and 3, which is still low. And again, I mean, if you look at the number of prior charges some of these people have, it's like, what? You know, like really, I don't understand. I can't explain it other than through a data issue. We even found possible typos in the Compass documentation from the company that makes Compass. They claim there's a linear dependence on age. As I showed you, we're pretty sure there's not a linear dependence on age. So anyway, we wrote this article attacking both ProPublica for explaining a black box wrong and Compass for being a black box where typos cause decisions. I wrote this paper, and the editor of the journal, it's the Harvard Data Science Review, the editor of the journal, the famous Zhao Meng, solicited articles, 6 articles, commentaries from famous criminologists and from essentially famous criminologists and lawyers. And one of these articles was actually from the company that makes Compass. And they wrote an absolutely scathing article saying that Compass is interpretable, which is pretty funny because if that were true, it would have saved me and ProPublica a lot of trouble. But in the mountain of criticism there, they admitted a couple of things that were super interesting. So they wrote, the authors, that's us, have taken a clearly informal description of the violence score in the practitioner's guide. And it wasn't intended to be a technical document. What do you mean it's an informal description? It's an equation. How much more formal can you get? Anyway, they wrote, discussions of appropriate variable transformations are beyond its scope. And we note that the skewed age variable is an ideal candidate for a normalizing transformation. And we thought, whoa, like it's like kind of a subtle admission of guilt there. And then in terms of transparency, they wrote that they're pursuing copyrights for the Compass scores. And we were like, whoa, you know, maybe we actually made a difference here. Anyway, just to summarize, scoring systems are good when you optimize them carefully, and typos are bad, which happens more often with complicated or black box models. And evidence suggests that we don't need such models in the justice system. So I thought, just to wrap up, I would just tell you about the problems we're working on in my lab right now. You've heard about scoring systems, but we've got a lot of other cool stuff going on. The sister project to scoring systems is the one on optimal sparse decision trees. And then we have a bunch of projects on interpretable neural networks for computer vision, and particularly with an application to mammography. I also have projects on neural disentanglement, where we're trying to have different concepts move through the network along certain pathways that go through certain neurons. I have a group working on dimension reduction for data visualization, where you take high dimensional data, project it down onto low dimensions to try to see what structure that high dimensional data has. I also have, I co-lead a lab on interpretable machine learning for causal inference, and that group does matching for causal inference, where the goal is to mimic a randomized control trial by finding treatment units and control units that are almost identical and trying to match them up so that we can figure out what the treatment effect is. And then the last set of projects is on understanding the set of good models and the importance of variables, because we don't always want just one best model. We might want to look at like a number of good models. All right, thank you very much.
I did not have the chance to introduce you, but I think now at this point it may be a bit too late. But I just want to say the lab you were referring to, in case you did not mention it. So it's the Interpretable machine learning lab, in fact, at Duke University. So and again, thank you very much for the talk. So now we'll have, so what we plan is to first have a comment by Ulrich Ivoji, and then we will have a Q&A with the public. So Ulrich is an assistant professor of computer science at the École des Technologies Supérieures, ETS, Montreal, in the software information technology, at the software and information technology engineering department. His research interests are in computer security, data privacy optimization, and machine learning. So thank you very much as well, Ulrich, for being here. So you can take maybe between 5 and 10 minutes to make your comment. And then if you want to respond, Cynthia, you'll be welcome to do so. So go ahead, Ulrich.
Okay, so thank you everyone, and thank you, Cynthia, for your talk. So I want to first start by saying I'm a big fan of your research, and particularly in the way you try to tell the community to explore other direction with respect to explanation. So as you start presenting I was thinking about, because most of the time people, as you already mentioned it in several of your work, that sometimes people hide beyond the fact that their model is, there is some proprietary information that they want to cover. That's why they're going to do black box. So do you, for example, if you want people to do more interpretability, then and also make profit, what will be the good way to, the good direction to explore for this kind of way? Is it looking more at how to protect the data that have been collected, or a way to somehow letting people use the model, prove that it is interpretable, but somehow at least how can we have some, if they want to make profit and also want, for example, the research investment to be like somehow make profit for this investment, what will be the good practice? And also, since the scoring system, they seem to also solve other issue, for example, with respect to low resource environment, where, for example, everyone is talking now that machine learning is consuming a lot of resources to actually train the model. So they seem to scoring system, since we can have them on a paper, for example, they seem to be like good to a good solution against this problem. And so one issue that can happen here is, for example, if we train the model right now and then we share it with some practitioner, how long it will take before the performance start decreasing, for example? I mean, is there any technique that are robust to distribution shift, for example, that will make sure that this technique can work, or are they also vulnerable to this issue with distribution shift in practice? Because you have worked with practitioners, have you observed this kind of decreasing performance when they are used in practice? And I also know that you work a lot on model multiplicity and Rashomon set of code models. And so you also mentioned in several of the work that it's very challenging to explore the set of these models. And do you also have this issue in scoring system? Because scoring systems, since they will be used to in very high stakes contests, how do you actually solve the problem? Because here, if we really want to consider the fact that we could potentially send people into jail, while there could potentially be other models that will tell a different story, then would you recommend to use like at least a set of scoring system to solve the problem, or how do you solve the problem in this particular context? And there is one question that I always want to ask you if I have the opportunity. So since I have the opportunity now, I will ask you, is how do you feel when because you do a lot of work to tell people not to use black box, but there are a lot of people that start by saying, yeah, black box model have vulnerability. By the way, Cynthia said that we should not use them. And here is a new explanation techniques that solve all the problems. So I just want to know, what is your feeling and how do you, I mean, convince the explanation, a post-hoc explanation community that is there really a chance that we will have post-hoc explanation that will somehow have some properties that is useful in practice, or okay, or is it possible to that is completely wrong? This kind of, I mean, this is another question I always want to ask you, so I ask it now. So thanks.
Wow. You are awesome. Those were amazing questions. Luckily, I wrote them down so I could answer them. Wow. Okay. So let me answer. I'll try to answer them in order. Okay. So how do we encourage people to use interpretable models? That's hard because companies really like to use proprietary models. So for example, the company that makes Compass, they're getting a profit because they're selling this model to the justice system, right? And so they're getting a profit, you know, and what's happening is that there are typos in those Compass scores, and people can't fight against it because they don't know that there was a typo. They don't even know what happened. And so I think for problems like that, where it determines people's freedom, I think we need a regulation, because you know it's just such a high stakes decision where you know, people are going to come and profit off of it if they can, but you know, the other side has no mechanism to sort of battle against it. So I think we need a regulation for those types of decisions that determine people's freedom. So that's something that I'm hoping to work on in the next few years, although obviously I'm just one person, so I need some help. Okay, so then the second question is, how do we preserve this idea of proprietary information, right? So I think that question maybe should be reserved for lower stakes decisions. So I don't think that for those criminal justice applications that preserve people's freedom, I just don't think that we need companies to create such models, because I don't think they're benefiting society. I think they're hurting people. And so for those ones, I don't think we should preserve proprietary information. But I do think it is possible to preserve proprietary information, but still make a model interpretable. So for instance, if you have a model that you can have a fairly large interpretable model, and then you can only show the person maybe part of it, right? That's something you could potentially do. You could say, well, you know, we are going to, I can't think of I need something that's like middle stakes, right? It's hard to think of something as middle stakes because everything's either like really high stakes, like loan decisions, or like, you know, whatever. Maybe some kind of loan decision where the loan doesn't really matter that much or something. But for example, we might say, oh, because you are this many years old and you've defaulted on your loan recently, that's why we're not going to give you another one, right? So some kind of, and it would be an explanation. It's actually like everybody who satisfies characteristics are going to be denied a loan. Okay, so that's one way to do it. How do you make models robust to distribution shift? So you have to continually test them in different locations. So for example, with criminal justice models, the thing is that we need to have those models to avoid using a different black box, which is a judge, right? We know that judges are biased black boxes, right? The judge is looking at someone, they look at their race, they're right in front of them person, you know, and you don't know what the judge is computing. So, so for those types of questions, we need to continually make sure that there's no distribution shift. And I'll give you an example that there is distribution shift in the criminal justice world. So for example, Compass has this very steep, well, it seems to have, I don't know if it does, but it seems to have, it's a really steep age curve, right? Really steep dependence on age that I showed you in that scatter plot. And the thing is that the age curves have changed over the last 10 years in different places. In fact, now it's actually fairly flat as a function of age, and nobody knows why. I talked to a criminologist about this, and he said that it might be because of video games. Like maybe people are staying in and like playing video games longer, and so they're not out committing crimes. I don't know. But there's a lot of theories, but that age curve changing over time, that's going to mess up the criminal justice models. So we have to continually test to make sure that the models are performing as well as they could, and maybe design different models for different locations. But that's I mean, hopefully models that are more interpretable will be more robust, right? Like the 2 helps 2B score was robust across hospitals, so that's good. But it doesn't mean that all models are going to be like that. Okay, 4th question. How do you explore the Rashomon set for scoring systems in particular? That is a really hard problem, and it's one that we're actively working on. For scoring systems, we actually have a mechanism to add constraints into our into RiskSlim, so that we can say, please don't pick the same model you picked last time. And so when we do that, we get a new model. And then we can put another constraint that says, well, don't pick either of the 2 models you saw last time. And so then we can generate lots of models by doing it that way. But it's not that computationally efficient. So we're working on better ways to do that. But it's a really good, important question, and one that we're actively thinking about in the lab. So I was really impressed that you asked that one. And then the last question, you're the only person who's ever asked me that. And I am really, really impressed that you were able to pick up on that, because it happens all the time. So the question was, how do I feel when people say that we should use black box models and quote me and use that as an excuse to explain a black box? Like, you clearly were not listening to anything I had to say. And they clearly didn't read any of my papers. And it just makes me kind of sad. But, like, it's basically, the thing is with someone like me, when you do that, I just get up and I go like, I need to go give more talks. Like, I need to get out there more, because people are just not listening, Yeah, it's really frustrating. I have to say that, I'm not sure. How should I feel? How would you feel if you were me?
Same, but yeah, it seemed like the field, like explainable AI, they want to have the reason to exist, so they want to show, okay, by the way, we know that you for example, a lot of people say explanation, we should not explain black box model, but still doing it. So I will be sad as well. That's why I'm asking, because I read a lot of papers that start by that, like, so it's
So I went to like some explainable AI workshops. In fact, I gave the paper on the Please Stop Explaining paper, the paper that's like Stop Explaining Black Box Models. I gave that at a NIPS workshop several years ago. And at that workshop, there was exactly like 1 paper on inherently interpretable models, and all of the other papers were explaining black boxes. And I've been looking recently to see, like, I don't even go to those workshops anymore, because there's no point, because it's all about explaining black boxes. So I don't know. I'm hoping my students will organize something that you'll be the first person we invite to speak, by the way.
thanks.
Okay, well, thank you very much. I think maybe it's time to open the floor for questions. So let me just explain briefly how we will proceed. So if you want to ask a question, just write your name down in the chat, and I will give you an opportunity to ask it when the time comes. If you write a question in the chat, then I'll ask the question for you. Je passe maintenant aussi en français pour vous dire, tout d'abord, toutes mes excuses pour mon retard et les problèmes là, en début de rencontre. Nous arrivons maintenant à la période de questions. Donc, on veut quand même rendre l'exercice facile aussi là, pour tout le monde dans les 2 langues. Donc, si vous préférez poser votre question en français, vous pouvez soit simplement écrire votre nom, et à ce moment-là, je répéterai votre question en anglais pour notre conférencière. Ou si vous écrivez la question en français dans le chat, je la poserai là, pour vous en anglais, et je traduirai la réponse dans l'autre sens si besoin est. So I was just saying, Cynthia, if people want to, in case you haven't picked up on that, if people want to ask a question in French, then I'll just repeat it in English to you, and you can respond in English, of course, unless you insist on responding in French, and then you're most welcome to do it. Okay, I think, so Martin, you did not write your name, but you raised your hand. So this is not what I asked for, but that's okay since you replaced me at the beginning of the talk and I'm already in debt to you. So go ahead.
Thanks, Dominique. Thank you very much, Cynthia. I have a general question about sorting system. What kind of task do they cannot do? I suppose that recognition algorithm, you cannot use voice recognition or image recognition. You cannot use scoring system. But besides that, what for instance, the YouTube algorithm recommendation system maybe could be made with scoring system. So how could you distinct different the task where scoring systems are useful?
So let me just share that slide again that sort of distinguishes between the different problems. So for scoring systems, they're really good for sort of high stakes decisions with tabular data. So in order to even warrant integer coefficients, you really have to have something where you want a human to be able to compute it in their heads. For like a YouTube recommendation system, that is low stakes, and humans don't need to compute that in their heads. So scoring systems are totally unnecessary for that application. But for like image processing, you would really want to use a neural network or like, you know, text processing. Like I said, it's possible to create an interpretable neural network. And what those networks do is they take, well, at least some of them. So the ones I've worked on, they'll take an image and then they'll take parts of that image and compare them to like prototypes of a specific class and say, well, because that looks like this, I think I'm going to give it like 3 points for this class. And because this looks like this, I think give it 5 points for that class. And so every calculation in the network can either be something that is visually verifiable by a human, or it's some kind of like linear thing, you know. Yeah, I hope that, does that make sense?
Yeah.
I hope it does. Okay, great.
Okay, thank you. So I have a couple of questions in the chat now. First question from Kate, who's a student in machine learning, and is asking, which topic area should I spend more time gaining a fluent understanding to better apply the kinds of methods you have demonstrated today?
So
which
I don't
topic
know,
areas? Yeah.
I don't know what your background is, but you might be able to read this paper. This is a paper that is a review paper that me and my students wrote on interpretable machine learning, and it gives 10 grand challenges. So if you're interested in interpretable machine learning, I would start there because it talks about what are the different types of techniques, like major techniques that you, or at least 10 of them. It doesn't cover the whole, you know, it's a huge field, right? It touches on like tons and tons of other fields, but it at least gives you 10 places to start. And then you could say, well, you know what? I like that. I'm going to go work on decision trees, or, oh yeah, I think I'll work on dimension reduction. And it gives you all the literature you'd need for each of the 10 areas to get started.
Okay, thank you. Thank you very much for that reference. Okay, there's a question now from Aaron Tao. So what is the best way to implement fairness in an inherently explainable model? Is it different than implementing fairness constraints in a black box model? And thank you for the answer.
Okay, so fairness constraints are much worse to like computationally to deal with than, well, not computationally, but constraint-wise. They're much more difficult to add in than interpretability constraints. Because with a number of the different fairness constraints, when you implement those into the model, you lose accuracy. Like you have to lose accuracy because they inherently trade off with accuracy. Whereas the interpretability constraints, you don't have to lose accuracy to embed those constraints. So the fairness constraints, they're much heavier constraints in a way. But for, so fairness is also one of those questions that the definition is also domain dependent. It's like interpretability. There's no one definition of fairness. There's no one definition of interpretability. You have to look at the domain and you have to be like, in this domain, this is what fairness means. You know, if it's fairness with respect to age, you know, okay, I'll divide it into different age groups and then try to figure out is each age group, am I constraining this model so that I'm behaving equally accurate for each of the different age groups, for instance. And like I said, those constraints are hard to deal with. But when you put fairness constraints on top of interpretability constraints, that's just more constraints. And so it just even makes it even harder. And I don't believe there's very much work at the intersection of the two. We did a paper recently on fairness for recidivism prediction, fairness and interpretability for recidivism prediction. And we didn't actually impose fairness constraints. We checked for them. We checked for different types of fairness constraints. So you could check that out if you want.
Okay, thank you. Before we move on, so I have a few questions, and there's one I think that is relevant to what we have said so far. So I've missed the beginning of the talk, but so what I've picked up when I joined is that, well, you use the expression black box or even interpretable, in fact, in at least two different ways. So a black box can either be a system where its underlying structure or values are not publicly known, which is the case of the compass algorithm, for instance, or maybe they'll change that because of your contribution, as you pointed out at the end of your talk. Or something could be a black box, not because we don't all have all the information in the system, but because it's inherently very extremely complex, as it could be the case with like a complex machine learning model. And so and then interpretable, I think you use it in these two different ways. So when you advocate for interpretable algorithm, it can mean, if I understood you right, whether to just make it public and make it accessible, or have ways to understand better which properties are correlated with what type of scores or decision by the model. And so you suggest that more interpretability is better. So clearly, but then it can depend on what type of situation. So there are clearly cases where having a model made public, in the sense that all the information about the way that it works would be known, could be desirable, but that's different than explaining a very complex machine learning model. So I don't know in which sense interpretable is the most important, or is there one way that is more important to you than another?
Well, to me, it's all about the stakes. If the stakes are really high, you've got to be interpretable. If somebody's freedom depends on it, or if someone, if it's like a loan decision where it deeply affects whether someone can buy a house or a car or something like that, that is something where it needs to be interpretable. Or if it's a life and death healthcare decision, like what the 2 helps 2B score is for, that's where it's better if the models are just plain old public. I think if the stakes are low, then not only do you not need interpretability, but you don't need even to really explain a black box unless you're trying to troubleshoot it. So those are cases where, some recommendation system for some company, I don't think you really need I don't think you really need either explainability or interpretability. On the other hand, so sorry, what was I going to get at there? If you so some of these explanation methods, they're trying to do things where they want to get very, very detailed information, but they don't want to they don't want to actually change the black box. So they want to figure out, for example, for medical imaging, there's a huge amount of work right now in saliency maps where they're just trying to figure out which pixels is this network paying attention to. Mm-hmm. And for those problems, you're just better off designing an inherently interpretable model. Like if you care to that level of detail, which factors are being used and how much they're being used, you should just bake that right into the algorithm. So I've never used Lime, I've never used CHAP, because those are problems where it's high stakes, and the problems where you need to use those methods are high stakes enough that I'm going to do, if I'm going to design a medical imaging model, I'll design it to be inherently interpretable.
Okay, so interpretable can mean either make an algorithm public so we know how it works, which is not the case of the compass algorithm, for instance. Or it could make like a complicated machine learning model less complex, or at the very least, we know like which properties or which inputs are more heavily correlated with some decisions of the algorithm. But I wonder, like in the case of like algorithms that do have a big impact on people's life, like the compass algorithm or criminal risk scores, isn't there a risk that if we make them more interpretable in the sense that they are made public, that will make it easy for people to game or cheat the algorithm, and it's the type of thing that we need to avoid?
Yeah.
Or in that type of case, when you say interpretable for the compass algorithm, what you mean is that at least within the organization, we should know how it works. But that may already be the case because their model is not that complicated. It's probably like a more classic statistical model.
Yeah, so the problem is that the people who are subjected to it don't know what it's doing.
Mm-hmm.
Right? So there you end up with questions of due process. It's like, well, you put me in jail because I had a high compass score. How did I get that score? Right? So there's an important issue there about who has access to that information and whether they can double check it. Yeah, so sorry, what was I going to go to that? I forgot. I'm sorry. I lost my train of thought there. But yeah, I think I think that's the issue. Is like, you know, it depends. It just completely depends on the application.
Okay. Well, thank you. Thanks. I think the next person in the list was Diego.
Hi, hello. Yes, I am. I'm hijacking Fanny's computer for this question. Can you hear me?
Yeah.
Oh, yes. Do you want to take your full name, maybe, or just so we know who?
Oh yeah, my name is
Diego. You are not Fanny Rancourt.
Yeah, my name is Diego Mopome. I am enrolled in the talk. I'm sharing Fanny's computer, or she's sharing it with me rather. My question is, when you were introducing two helps to be, you mentioned that if there were sort of mitigating factors, physicians could sort of calibrate the formula for to obtain the score. Could you speak a little more to that? Is it that you're sort of limiting the scope of the model and leaving the sort of the edge cases out of it, or is it something else?
Oh, no. So very often, you know, a database will only contain the information that is being recorded that has been recorded for the training set. So there could be some information about patients that are like, maybe the patient's unusual. There's a lot of unusual circumstances for patients, but also maybe like this hospital keeps track of more information than that other hospital kept track of, and the model was built from that other hospital's data. So it just might just be that the database just doesn't, literally the database has no information about this one factor that the doctor knows is important.
Okay, so it's both. And is the model built to account for these potentially missing factors, or?
No, it's really hard to account for a completely missing factor because you can't use it for prediction, right?
Okay. Okay, well, thank you very much.
Sure. Mm-hmm.
Okay, thank you. Ulrich, do you want to step in at this point? Is there something you wanted to add to the discussion?
Oh, I just have one comment when you were discussing about the intersection between interpretability and fairness. I was sharing one link in the chat where we try to conciliate both interpretability and fairness, and using your work, we use one of your paper corals, and we try to integrate fairness into the Blanche and Bound framework, and we have some results, but as I said, it is there is not too much work in this intersection right now, so just want to mention.
So your work is probably one of the very first works that actually incorporates constraints of both fairness and interpretability. That could explain why I think I've heard your name before.
Probably.
I know your name, but I didn't know where. But that's probably where. Did you publish it?
Yeah, we published one. I can send you the link. Yeah.
I think I've seen it. I think we may have cited it, and I was thinking I've seen that name before, but I didn't know where. Yeah. Okay. Yeah. So I mean, the latest iteration of corals is called Ghost. It's this algorithm. So we took corals and we extended it to full-blown trees. So just in case you.
Yeah. I saw that. I'm a big fan of your research, as I said, so I know that.
Oh, that explains all the questions. I was like, who is this guy?
Okay, well, now I have a question from Daniel Cote. So it's a question around consent on the usage of data. So he's asking, should we be concerned on how our personal data are used without our consent in black boxes? or is the benefit outweighs the concerns in terms of getting better accuracy?
Oh, that's a really difficult question to answer. I mean, I'm more aligned with the sort of private, like, for instance, I think a lot of my personal data goes out to big tech companies that I want to be able to control it, right? And I don't really want them having a lot of my data because I didn't agree to it, right? I didn't agree to whatever company selling my data for their own profit. And I didn't agree to Clearview AI taking my images off the internet and using it to train their facial recognition algorithm, right? At the same time, I think healthcare data should absolutely be made available so that we can use that data to design better healthcare models. So for instance, in mammography, we can't find publicly available data. And there's so many people who have breast cancer or who potentially have breast cancer who'd benefit from having health data being public obviously without people's names on it, without people's, location information on it. So made available in a privacy preserving way, that I really don't think that sort of healthcare, the level of preservation of the healthcare data, I think is unwarranted and it hurts human health, right? So it's to me, it's shocking that there is no big public data set that we can use for training deep learning methods for mammography. So what happens now is all the companies basically have to make deals with all the hospitals and buy all the data so that they can train their deep learning models for mammography. I don't think that's okay at all. And I definitely think privacy needs to be sacrificed for that one. But like I said, I think it can be done in a privacy preserving way.
Thank you.
Yeah, I hope that answers that. Yeah.
Perfect.
Thank you, Daniel and Cynthia. Now we have a very long question from Gaël Varocco about parsimonious models and so their advantages. So yeah, as you suggested, Gaël, perhaps it's best if you ask the question yourself.
Sure. Thank you very much, Cynthia, for the thought. It was very, very interesting. I thought you made a very convincing point on the fact that some models that are easier for human beings to reason from can work as well as more complex ones, and we should prefer them. I've been less convinced on the fact that we can do without black box model interpretation, and the reason, based on my experience, is that I find that often human beings, non-experts, get it wrong even on super simple models. So something like a linear model, they get it wrong because they don't understand conditional relationships in the data. And the other thing is, you've also shown us that model-based interpretation is based on modeling assumptions, and I think the ProPublica example is a good one. So I'm lucky to have you in front of me. How would you reply to such a challenge? Thank you very much.
Okay, wait, let me see if I understand the challenge.
My point is, I think we still need a black box model interpretation because they're more robust to some misinterpretation and some mismodeling.
I'm not sure what specifically you're referring to. So you'd rather have like Compass with an example, but see, like the problem with explaining black boxes is like you think they depend on variables that they don't, so I'm not sure what specific, and I give you an example of that, so I can't.
Does it matter that they depend on variables that they don't, if those variables are super correlated in the data?
Yes. Like I gave you an example of the ProPublica article that caused this huge scandal by declaring that Compass depends on race in addition to age and criminal history. Right? This was a huge scandal, and it's not clear to me that it was warranted. It's because they explained a black box wrong. I think the scandal should have been different. I think the scandal should have been, gosh, we were using black box models in the justice system. I mean, you also have all these like medical examples where they have these explanations that are like saliency maps, and like the saliency maps are highlighting the wrong part of the image. It's like, no, the network's looking over here, but yet the explanation says it's looking over there. It's like, what? What? That's not right.
Okay.
Oh, we can barely hear you.
Yes, I don't know if you... Are you done with your question, Gaël?
Is it better now?
Yeah.
Yes,
Okay.
it is.
Yeah, but is your answer that we need better research in model explanation, which is difficult and current research isn't satisfying? I agree. Because the example of ProPublic, I'm still not convinced. Basically we have highly correlated variables, and I think it's going to be a debate between experts on which of them the explanation is a good one.
Well, but why bother? You can just throw compass out and replace it with something tiny.
Sure.
Can I rephrase that in a different question, perhaps? It's hard to think of a situation where it would not be better to have more information about like the inner functioning of a model, see if it's kept from the public or that type of thing. But would there be cases, Cynthia, where using variables other than the one that are used as inputs to the model would be more useful in explaining the behavior of the model, because they track better some of the underlying assumptions that take place within the model? I don't know if that was clear, but
yeah, I mean, I think you could, calculate various statistics of the predictions, that's fine. But you shouldn't think that you're necessarily explaining what the model is actually doing. Like if you said, I'm going to approximate this model by another one, great, that's fine. You have a nice simple approximation. Just don't call it an explanation because it's not, it's an approximation. Or for instance, you could take, let's say you have an interpretable model it's global interpretable model, but it's kind of big. It's kind of like bulky, uses a bunch of variables. You could create a simpler model that would say, well, for this one individual, everybody with factors similar to this has the same prediction, something like that. And I think that could be useful because you could say, well, yeah, you were denied a loan, but everybody who is your age who has a very short credit history is also denied a loan. Everybody like you is denied it. So it'd be like a simpler kind of explanation you could provide to that person. But you have to be very careful on how you use these things because they better be consistent with the black box, and you better not say that that's what's actually in the black box when it's not. You got to be careful with it.
Okay, yeah, great. I see that there are not that many people that want to ask a question, so I may throw a last one in, and if we're done with question, we'll end the session after that. Of course, I had still zillions of questions, but I don't want to hold you for too long. But the question would be, because it's quite related with what you just said, so one of the issue with black box algorithms, whether because they're kept from the public or they're just too complex to be explained, is that then organization can use like fake explanation to give the impression that their model are fair or not biased in ways that would be problematic. And we've seen cases of that. So I was curious, given that you're such an expert in the field and you work with these things all the time, do you have examples of very good cases where we've provided explanations of black box, so black box explanations of an algorithm that were done very well? And also maybe examples of the worst cases or the very problematic cases. So I know there are issues, for instance, and those are things that I've worked with Ulrich and Sebastian Gans, who joined the conference. There was some issue with Facebook doing that with some of its algorithm at some point. So we have examples of very good cases and bad cases of these types of black box explanations.
Can you tell me the Facebook one? I'm really curious to hear what they were doing.
Well, maybe Ulrich can say more about that.
There are some work on recommendation. I can share the reference. It was more about the way the recommendation are done. For example, when you read a post and then you ask to have an explanation on why you received this recommendation. It's basically explanation of in recommendation system. And there have been some investigation that show that actually the recommendations are based on some demographic aspect that should not be used in reality, and this kind of, I can share the reference with them.
That would be really interesting. Yeah, I'd love to see that. So I think I gave the example of Fico scores, and I don't know, so I paid off my loan, right, and for my house, and then my FICO score went down. Just went, which made no sense. It's like, I just paid off the loan. Like, why is my credit score going down? It should go up, right? Because I paid off the loan. So they gave me an explanation, and they said, oh, you don't owe money to enough people. You don't owe money to enough people, and so your score goes down. I'm like, well, yeah, I don't owe money to very many people. Like, that's true, because I just paid off my loan. And then, you know, they gave me actually even contradictory reasoning for why, you know, they gave me two things that I needed to do. Like, the first one was like increase the number of people I owed money to, and the second one was something like you need to decrease the number of open accounts you have, or something like that. It was like completely contradictory. So that, yeah, I'm not a big fan of those FICO explanations. I don't think they're very good.
But is that a bad explanation? Because it's possible that they really provided true information about the way that the algorithm, like the Fico score, works, and what will correlate with a higher or lower score. So in that sense, the information was very accurate. Now maybe it raises issues of fairness, okay? And it raises issues about the score, but in terms of the explanation that was provided, it was pretty close from the way that the algorithm functions.
I have no idea how the algorithm functions, and I have no idea why I was given two pieces of advice that were exactly doing the opposite of each other. Like, should I get another credit card? Because then one of the, you know, then one's going to go down and the other one's going to go up. Like, it doesn't make any sense. What should I actually do? So I was just glad that I was already paid off my loan. Let's just say that. Glad I didn't need a new loan anytime soon.
So I shared the link in the chat, so maybe it can be interesting.
Oh, cool. Thank you.
Okay.
Wow.
Well, thank you then. Thank you for the example also, and thank you, Cynthia. I think you had many engagement this week, so thanks for being with us for this engagement, and thank you everyone. So we have more talks in the series this year. So we have two conference talks in March 2022. So one by Sylvie Delacroix and one by Suzanne Landau. So Sylvie Delacroix's talk is on March 10th. And Suzanne Landau's talk is on March 31st, but it's possible that we will have one more talk before that also. The information will be posted on our website. And this session is also recorded, so we should be able to put that on our YouTube channel as well, in case you want to have a look at it. So thanks again, everyone.
Thank you.
Thanks, Cynthia, Ulrich, Martin,
Thank you.
and Christine.
Okay, thank you.
Have a great day.